Dear members of Dystonia Europe, it's my great pleasure and honor to be here. And it's not the first time that I'm attending one of your conferences. And as always, I'm incredibly impressed and also inspired by all of what you do. And I would like to thank you for that before I even start. Thank you for the kind introduction. I have to admit that, a lot of the credit that you just mentioned actually goes to other people. And so I will mention and show them to you while I go along. So yes, I have been asked to talk about DYSTRACT, which is a relatively recent, it's only 2 years old, German research network. And I will give you some of the details over the next 15 minutes or so. Before doing so, however, I would like to go back again to one historical slide. We had a beautiful talk earlier today, and I learned a lot. Thank you for that. But I cannot resist mentioning Hermann Oppenheim to you. As you know, he coined the term dystonia, and we heard this before. He was one of the people that were adamant that dystonia is indeed an organic disorder. Unlike his peers, including very eminent people such as Charcot, who thought that this was a form of hysteria. And so I think he should really be credited with not only coining the term, but really fighting for the truth, and that is dystonia is an organic disease. And not only did he do that, but I don't know if you read his actual paper, he already, and this is here in German, but many of you I'm sure can read this, so he already speculated that hereditary burden, so a familial genetic cause, plays probably the major role. So even in 1911. So let's now turn to a few videos. So I think this explains very beautifully, without me having to say that much, that we have a big need for networks. And one of those networks are you, and another one of these networks is DYSTRACT here. And so you can see all of these patients I'm sorry, have dystonia. And not only do they have dystonia, but they have a rare form of dystonia, and that is dopa-responsive dystonia. I'm sure that many of you have heard about this particular form. Maybe there are even 1 or 2 patients among us here who have that. The important thing about this particular form, it is a genetic one, inherited, is that it is very, very well treatable. So we must not overlook it. And why could this be a problem? Because as you can see here, the prevalence of dopa-responsive dystonia, when you read in the books, you're told that it's 1 in a million. But all of those patients, and they are not all of the ones that we see, we actually see 23 currently at our center. They live in and around Lübeck. And so, and as you may know, Lübeck is a relatively small city with 220,000 inhabitants, so it can't be that rare. So I think some of the prevalences are really underestimated, and we need to really work together, and we need networks to be sure that we know how common dystonia really is so that we don't miss it. And so this is now the DYSTRACT Consortium. And really the head, the speaker of the consortium, and I'm only the deputy speaker, is Jens Volkmann. And you can read all the names of the principal investigators. But of course, the network includes a lot more people, and you will see pictures of them as we go along. And the DYSTRACT Consortium tackles 10 different projects that are all related to dystonia. The first one, led by Jens Volkmann, is actually a clinical trial. And I will now only mention them very briefly and then go through them in more detail as we go along. The second one, led by myself, is a German dystonia registry. Then we have an IT platform, of course, because there's a lot of data. We have IPSC models. Those are induced pluripotent stem cells. I'll come back to that later. We have a genetics project. We have rodent models, both mice and rats. There are physiological projects, and also both in the rodent models and in people. And there is a special project on musicians' dystonia. And Alexander Schmidt, sitting at the very end of the room, just arrived, and you will hear, I'm sure, a beautiful presentation by him tomorrow about the details of musicians' dystonia. So let's go now through those 10 projects. As you can imagine, I'll have to do that relatively quickly, but I'll be very happy to answer questions that you may have later on. So the first one, led by Jens Volkmann, is the StimTox CD project. So this is a clinical trial. As you may know, only a minority of patients with cervical dystonia is really happy and fully content with the botulinum toxin treatment. So the idea of his project is to demonstrate that symptoms, especially of more severe cervical dystonia, can perhaps be better controlled by deep brain stimulation than by toxin injection. and that this is a sufficiently safe treatment. And with this, you would like to enable patients to make a more autonomous decision of what kind of treatment they want to have after careful medical counseling, of course. And you won't be able to see, but this is a very complex scheme of how the trial is designed. We're turning to the second project, which is the German Dystonia Registry. And again, I think it cannot be overestimated how important it is to collect the data. And so this is the idea that we had for this project. And again, lots of people are involved. You can see them here. And so the aim is to collect 3,000 patients in Germany with dystonia and to screen them for mutations, because we want to know how many of these patients can be explained based on a genetic origin. And then we would like to provide a resource also of the clinical data and the biomaterials that we collect. Thank you so much. Yeah, I had a bit of a cold. Thank you, that's great. And to serve, so basically this is a resource also for all other researchers, all of the consortium and outside the consortium as well. For example, Rose, where she may want to use some of these cells, and so that we can make them available. And so this is what we've done. We have 5 main centers in Germany that collect the samples, but there is a growing number of sub-centers. You can see them here on the right that also contribute samples, and you can see nicely that we are picking up speed here, collecting our patients, and so far we have collected 300 completely new samples, new patients, and 2,000 old ones, so we're making good progress. And I will show you more about the biomaterials and the genetics a bit later. The IT platform, obviously also very important. We have a central information office. We have a remote data entry system also for the clinical trial. Obviously, it's very important to preserve patient confidentiality. And while I'm mentioning this, I would like to remind you that the videos that I'm showing here cannot be put permanently on the internet, so they will not be visible there forever. So, and also we have a content management system for the DYSTRACT website that is indicated here. All right, let's turn to the fourth project. So this is now the IPSC Platform. And I'm sure that many of you have heard that we have this beautiful technology of induced pluripotent stem cells. So how does this work? We take a little skin sample and grow the skin. The skin cells are then called fibroblasts, and then turn them into a stem cell from the very patient that donated that little piece of skin. And this is beautiful because then the stem cell can be turned into a neuron. And as you know, it's very difficult otherwise to get hold of neurons, because obviously we cannot, really take brain cells from a living patient. So this is a very nice way of getting at tissues that are otherwise inaccessible. And so the idea of this project was really to build up a biorepository of these fibroblasts and iPSC lines from patients with different genetic forms of dystonia, because, and we heard this just from Rose Goodchild, that it's so much easier for us researchers to, at least we have a better, to tackle dystonia when we know a bit more about how it is caused. And so this is what we have done so far. I think this is a relatively impressive list. So you can see on the left, this is all sorts of different monogenic forms of dystonia. And we also have, for comparison, controls and people without gene mutations. And you can see we have already collected 48 of such fibroblasts, so skin lines, and we have turned 37 of them into these stem cell lines. And I've just shown you an example here how beautiful the neurons look that we can make out of those stem cells. So the upper picture shows you some dopaminergic neurons, and the lower picture shows you some medium spiny neurons that are also very important in the basal ganglia. Fifth project is on genetics. So as I mentioned, we expected among all those patients that we would find quite a number of mutation carriers that have genetic causes of dystonia. We thought, and it's true as our data show, that this will be only a relatively small subset, but an important one to recognize, and especially when it comes to more qualitative treatments that we're hoping to develop, it is important to identify such patients. Also, a goal of the genetics project, led here by Katja Lohmann, who is actually one of the recipients of the David Marsden Award. You may have seen her picture earlier today, together with Thomas Gasser in Tübingen, was also to find new dystonia genes. And I would now like to show you what we found. So we first established a gene panel that includes 29 genes for dystonia and also for Parkinson's, because as we heard before, there's overlap as well. And we have so far analyzed 1,000 patients. We found 28 carriers, so about 3% of pathogenic variants in all these different genes, and we have heard beautifully about those different genetic disorders before. And we have also found 75 carriers of variants of unknown significance. So in those 75 cases, we don't know whether the variant really causes the dystonia, but it could be, for example, a risk factor. And taking together the 75 and the 28, then this would come up to a percentage of about 10% of the entire sample where we can find some possible genetic contribution. And this is an example where we found a new gene. So this was a de novo mutation in the GNB1 gene. This is a little girl who presented and this is actually also what we found in her. And hopefully this will not, okay, I'll just go further not to cause any more problems. So in her we found a non-inherited mutation that caused her dystonia. And this is actually a relatively common finding of the dominantly inherited forms of dystonia, or rare diseases overall even. About 70% of the patients have new mutation that they newly developed. So they may not have a positive family history. And that, I think, is an important finding. I would now like to turn to the rodent models, and these are being developed by Michael Sendner and his team here, and he wanted to focus in particular on mutations in TAP1 and in GNAL, and I'm sure this is also interesting to you, Rose, that these models now exist and that there is room for collaboration. And I'm not a mouse geneticist at all, so I will go over this very quickly. I just wanted to share with you this data showing that the mice have been developed, both the ones with GNAL mutations and TAP1 mutations, and that they do have a phenotype. So they show abnormal hind limb clasping and positioning, which could be a sign of dystonia in these mice. And they develop this over time, so at the age of 6 or 7 months. And they have problems in several of the behavioral tests that are being applied to them. The next project, led by Chi-Wang Ip here, also deals with the rodent models. He, however, works with rats, and he's particularly interested in what triggers dystonia. As you know, dystonia can come relatively out of the blue, and we often try to understand, what are the triggers that made it happen. And so this is what he's trying to study. So what he does, he has a DYT1, for example, model here, and then he injures those rats with a nerve injury, and then after that, the rats develop dystonia, and he's studying the triggers and the consequences of these triggers in these animals. Now we're turning back to humans. So 2 groups of the consortium are very interested in studying actually the human situation in the brain with a variety of very interesting methods. And one of these I would just like to show you here. And this is now talking about myoclonus dystonia. Again, we have heard about myoclonus dystonia today before. Myoclonus dystonia is one that is accompanied by jerks, quick jerks, myoclonus, and it responds very beautifully to alcohol. So when these patients drink alcohol, and you may know people that have that, the dystonia and especially the myoclonus usually goes away. So one interesting question to us was, what is that consequence with the alcohol, and what do we see in the cerebellum? Because we knew that in myoclonus dystonia, the cerebellum plays also an important role. So basically what was done, we used a cerebellar learning task, and in red you see, this is on the left, in red you see the line of the myoclonus dystonia patients, and they don't learn as well as the controls in black, so there's quite a bit of a discrepancy there. However, when you give them alcohol, and we had ethics approval, this is only done in people over 18, So when you do this, you see that this learning deficit goes away when they drink alcohol. We still don't understand how this all works, but I think it's an interesting finding. Another project, also within the same group, also deals with cerebellar learning, because we now understand that the cerebellum is really important in dystonia. And it turns out that patients with cervical dystonia show less sequence learning in a motor sequence learning task. However, for example, in a different task, they perform just as well as the controls. And so we're trying to dissect exactly what goes wrong. It's a bit of a tedious process, but we have to do this, brain area by brain area, and this is done in these kinds of studies led by Alexander Münchau and his team. And in a similar fashion, Andrea Kuhn here, she also is interested in the networks of the brain in the context of dystonia. And for this, she uses very sophisticated techniques. She uses, again, intracranial stimulation through deep brain stimulation and also magnetic encephalography. And this is a very big machine that you can see there that many labs, very few labs have available. And she has also some very intriguing findings, and I could show you, I could just talk a whole hour just about her findings. What is interesting is that she can correlate symptom severity with the activity in the pallidum, and so that we try to really connect all the dots to better understand what causes dystonia, what makes it worse, how can we predict perhaps the disease course. And now I'm coming to the last project, Musicians' Dystonia, and like I said, you will hear more about this tomorrow. In the middle, this is Alexander Schmidt, and on the left, this is Eckhard Altenmüller, Daniel Scholz, who work on the project led by Eckhard Altenmüller, and you know him, I'm sure he has been a speaker here as well before. And they're interested in clarifying the role of the triggering factors of musicians' dystonia, and to also come up with a new classification of musicians' dystonia. This is just a short video of a patient with pianist cramp. We can't hear it, but I think you can see he's trying to play a scale, and his fingers of the right hand, they just cramp and they curl involuntarily, and he's a professional pianist, so you can imagine that this very severely interferes with his piano playing, and this is the left hand that is perfectly fine. So what are they looking at? They are looking at all the various potential triggering factors and want to establish a mathematical model of those interrelationships. So for example, how does the time when you start learning an instrument, how does that interact with overuse or pain or other things, or anxiety disorder that you may develop over time? And here you can see a relatively simplified model that Eckhard Altenmüller sent to me to present to you today. So there's basically this interesting observation that apparently when you start very early learning your instrument, you actually are better off and your skill level is actually higher. And this is the green line. If you start a little later, this is after the age of 6.5, the blue, you are at a slightly, on average, of course, on average, at a slightly lower skill level. Of course, there are wonderful musicians that start late, but on average, this is what they found. And with the musicians' dystonia patients, they start out in red beautifully, and then they practice a lot, and they have a lot of also problems with overuse and potentially even trauma. But then, as soon as the dystonia kicks in early adulthood, as you can see, the skill level obviously goes down, and most of the musicians' dystonia patients that are professional musicians really have to terminate their careers. So with this, I'm at the end. I just want to share a few exciting perspectives with you, what we want to do next in the context of DYSTRACT. And one is a database that I wanted to share with you that we have developed, and this is online, available freely, and you can choose genes. For example, TOR1A, DYT1, it will then give you all of the cases published in the English literature worldwide. And also, just upon a click, it will give you an overview and statistics of all of the different symptoms that your patients have. It also gives you the age of onset of these patients, the ethnicity, what kind of mutations they have. So all of that is available online, and we think this is an important part of the project to make data available to the community. Another exciting part of our work is genome editing. You may have heard that it is possible now relatively easily to edit the genomes. And we have done this here in the context of a form of dystonia that's called X-linked dystonia Parkinsonism. And what we have done, these patients have a large mutation. It's almost 3 kb long, so it's a really large insertion that doesn't belong there. So we have cut that out with this gene editing method. And as you can see, perhaps in this lower scheme here, we have been able to normalize in the people where we have cut out the mutation at the stem cell level. We have been able to normalize the transcriptional problem that these cells previously had. So this is a very nice proof of principle that this is possible, and that we can hopefully use this also later. This is a longer term perspective, but later also for therapeutic applications. Another very interesting and hot topic that we are interested in is the fact that not all mutation carriers develop the disease. Indeed, for example, in DYT1 dystonia, only a third ever manifest the disease. 2/3 of the mutation carriers remain healthy throughout their life, but they can pass on the mutation. So what was found out, and we were proud of this a few years ago, is that if you have a mutation in the TOR1A gene that Rose also talked about, like I said, your penetrance is down to about a third. If you carry another variant that some of us here carry as well, then you're protected. And if you have them together, your penetrance goes down to 3%. So you're almost completely protected against developing the disease. And to find mechanisms like this and to use them also for genetic counseling is another role of the DYSTRACT Consortium that we would like to fulfill in the next period. We're also turning to zebrafish models. We heard about Drosophila models. We're turning to zebrafish models. This is a patient with DYT4 dystonia, type 4 mutations, who has a very unusual dystonic gait. It's called a hobby horse gait because it looks a little bit as if you were riding a hobby horse. And we have now developed these fish that have the same mutation as humans, and I would like to convince you now that they also have a bit of a hobby horse swim. And I will show you the other fish that swim normally below. So we'll see how well this works as a model. And of course, these fish are meant to be used also for drug screening and other purposes like this. Finally, we will personalize. This is a patient with X-linked dystonia, Parkinsonism. YT6 dystonia here, this is a patient also after treatment, after stimulation, do not respond as well. So we understand more and more that genetic factors also shape treatment response. And with this, I'm at the end, and I would like to thank you for bearing with me and to run through 10 different projects. And this is the whole team. We met in Lübeck not too long ago, and I would like to also thank the funders, because this is really a study funded by the Federal Ministry of Education and Research, and it's great that they fund such a project dedicated to dystonia. And of course, I would like to finish off by congratulating Dystonia Europe on your anniversary and by thanking you for inviting me to present. Thank you.